Just trying to move this away from here. Anyway. Okay, good. Thank you everyone for joining us in the September monthly session for Dashu online session. And today, very honored, very happy, we have invited our friend Peter to present us a very trendy topic about how to utilize external data such as real-world evidence data to be part of your clinical trial design, right? Single arm trials with synthetic control arm. It is a very hot topic, especially for us, some of us in industry. We truly want to be more efficient, productive, and also, of course, if we don't have to use all the patient in the randomized trial, that would be a perfect way to go. But definitely there's a lot of a methodology perspective and even operational perspective. People haven't gathered all the answers yet. So hopefully Peter today will give us a great talk and for us to think more in depth in this perspective. Before I go to the topic, I really want to go over our Dashu a bit to really thank all the volunteers and also explain what we do. So Dashu is a non-profit organization, and I was one of the co-founder, and I work in the industry as a head of a biometrics team. So a few of us get together a few years ago, really want to help the community shape more innovative ideas and exchange information together. So it's definitely all of us are volunteers here for that purpose. So we created Dashu and has been working on so many different seminars every month. We have online seminar to invite experts, KOLs, to present us, to share their newly developed ideas or their design perspective or any methodology. So we cover data science, we cover biostatistics, bioinformatics, deep dive, AI. So any of your interest topics we cover. We also help students or junior data scientists or statisticians to develop their career. So we have different career development trainings. We work with different society to establish the conferences together. All of those are truly a great effort. Without any of the volunteers from this community cannot happen. So we do, ask all of us, feel free to join us to lift this big community up for the benefit of everybody in the community. So this is a free membership. Anything you enjoy, you join us and you will receive the email blast of monthly seminars and anything we're organizing as I just chatted. And here's the contact information, info@dashu.org. And we also have a YouTube link with most of the presentation if speaker is okay to release, and on LinkedIn, WeChat, all the connections. So feel free to join us. I really want to thank all the volunteers have been working and helping me and some of the leadership members to make this happen for 6 years now. We have a lot of events occurred. Each of them, you can see the smiley face, and we have different network events also between the volunteers. They also help each other grow in their career or even just friendship. So it's a really fun and friendly and interesting group we have here. Feel free to reach out to me or anyone in the email you see Dashu info to join us and to work on it together. So with that being said, I really want to introduce our speaker today, and Professor Peter Muller. And he is a big name already. I'm not going to read all his long bio one by one, but just let you know he has been working in the academic areas such as Duke University for almost 10 years and transitioned to MD Anderson Biostatistics Department about 10 years. And the current 10 years, and Peter, I was just joking with you, every 10 years, it's about time you change to a big faculty position. So he brings definitely different big academic center experience already every decade. So now currently Peter is a professor of statistical mathematics at Utah Austin. So he has over 150 referred articles in statistics, biostatistics, and other journal. And he is elected fellow of Young ASA, also IMS, ISBA. So definitely very prestige, well-known statistician in the field. And his expertise and interest of the research actually is pretty wide too, mostly focused on non-parametric Bayesian methods, simulation-based methods, optimum design, and multiple comparison procedure. So he's extremely interested in applications, biostatistics, bioinformatics, including particular Bayesian clinical trial design, hierarchy models, population PK/PD models. So today, I'm very honored to have invited Peter to join us, give his most recent research on using external data be part of the clinical trial design. So with that being said, maybe Peter, I'll give the floor to you for your presentation. Thank you.
Thank you. Thank you for that kind introduction, and thank you for the opportunity to present here. I'm very honored and humbled. Can I have the screen, please? So I guess if I just share, I can.
Yeah, I'll stop sharing, then you can go ahead share. Perfect.
And you should see my slides now.
Yeah.
So thank you very much for joining today. I want to tell you today the following story. On this title slide, you see on the left figure, the left part, I think you can see my cursor, right? That left block, that is a current single-arm trial. It's a current single-arm trial in neuro-oncology at MD Anderson for glioblastoma patients. And the idea is that we want to augment this single-arm trial with a control, where we plan to build the control by using data from historical trials. This big block here, this big block of data, those are data from historical trials, and we want to somehow use this available data to synthetically create a control arm. On this, in this figure, on the horizontal axis are patients. So there's a relatively small number of patients in the current single-arm trial, and there's a moderate number of patients in the historical data. On the vertical axis, you see some of the covariates, categorical covariates with the different color shading showing the different levels, and white showing missing data. So one of the little themes, kind of a footnote, but an important one of the little themes of our discussion will be how to deal with missing covariates, or simply covariates that are not recorded for all kinds of reasons. Might not be appropriate to treat them formally as missing data. So I'll tell you about one method to achieve this construction of the synthetic control arm. And here the center panel tells you a short summary in a little stylized cartoon of what we are doing, what we're up to. The red, what you see here is two mixture models, a red one and a green one. The red mixture model is what we fit into the data for the current single-arm trial. The green mixture model is what we are fitting to the data from what we are fitting to the historical data. One twist here is, one thing to notice is, do you see it's two different mixture models, but they actually share the same atoms. These two mixture models, they share the same clusters. So we really say we are setting up two mixture models with common atoms, with common cluster locations. And once we do that, we can do the following trick. Like we want to have a population like the red mixture to be constructed using the green patients. Just staring at the picture, probably all you have to really do is reweight patients with some ratio of the red and green weights, and that's exactly what we shall do. And we'll do that in a coherent way, taking care of all the relevant uncertainties. So we'll fit common atoms mixtures, and ratios of the weights will facilitate thinning out of the data or weighting of the real world data, so that we can claim that we have now equivalent patient populations. Like after the weighting or thinning out, we can claim that now the weighted historical population is equivalent to the current single-arm trial population. Equivalent in the sense that FDA might even accept it as an equivalent patient population and as a reasonable choice to construct the control arm synthetically. One way to prove that is we can simply try to merge these two patient populations and try to classify them. If your favorite universal classifier fails to classify them back into red and green data, then that would be success. Then you have successfully created equivalent populations. So in this little picture, actually a simple 45-degree line, that would be victory. The curves show ROC curves for the classification. If the ROC curve is just a 45-degree line, that means it's only as good as coin flipping, or in other words, you can't tell the two apart. The blue line, that would be failure. Then we did not manage to make them equivalent. That's the executive summary of everything that's coming up now. All what's coming up now is I'll talk you through the details, and I think many of you can probably kind of impute what the details will be, but I'll still do it in all details, step by step. This is joint work with Noerit Chandra, postdoc here at UT, Abrasaka, one of my colleagues, and Ying Yuan and John de Groot at MD Anderson. Ying is in biostatistics at MD Anderson, and John de Groot is in neuro-oncology. So I don't have those many slides, so feel free to ask occasionally. You can put questions into chat, and Sammy, if you can watch the chat and just alert me if there's any questions, then I can try to address some of the questions as we go along.
Yes, we will do that. Thanks.
So here's again repeating the title slide. You can see one of the issues is in glioblastoma, for a variety of reasons, investigators use single-arm trials. One of the reasons is simply enrollment, even in a big cancer hospital like MD Anderson. Another reason is that patients and treating physicians prefer treatment because there is still a lack of effective treatment options in GBM. So for a variety of reasons that are discussed in this reference that I cite down there, GBM trials are often single-arm trials. And the issue arises, wouldn't it be nice if we could enrich that single-arm trial to a two-arm trial by adding a control arm, an artificial control arm? One option is to construct such a control arm on the basis of historical data. This is a single-arm trial going on in neuro-oncology in MD Anderson. They have a steady stream of carrying out such trials, and they have a good record of historical trials. Historical trials going back only a few years. You don't want to go too far back, lest you might run into issues when standard of care has changed and you have problems with different standards over time. So here's what we want to do is we want to use that blue historical data to create a control arm to add to the red current treatment arm. Throughout, I will use red T to indicate the current single arm trial, and blue C to indicate the historical data which I want to use to build the control arm. This is a very popular theme. We're obviously not the first ones to try that. One of the reasons is recent legislation. There's like the 2016 21st Century Cure Act, or Clinical Care Act, I think it was called, which directed FDA to explicitly to consider what they refer to as real-world data, and that has opened opportunities. That has opened opportunities, although still randomized clinical trials, of course, remain the gold standard, simply because in a randomized trial, you can cleanly attribute difference in outcome to the treatment. But there are many situations like our scenario here, where for a variety of reasons, you don't have a randomized trial, and then it becomes attractive to consider real-world data. Real-world data could be any conveniently available information relating to the disease and treatment of interest. Typical examples are historical data, as we have it here, could be insurance data, could be repository data, anything. Real-world evidence refers to the information that we can extract from the real-world data. And based on that legislation that I mentioned before, FDA is actively encouraging or they accept the use of real-world evidence in clinical trials. When Janet Woodcock was still director of FDA CDR, she said, we have this quote here, affirming that FDA will work with stakeholders to use real-world evidence in clinical research. And one of her predecessors is FDA Commissioner Stephen Hahn, also commented on the use of real-world data. Ignore the details, just want to indicate there is real encouragement from the side even of regulatory agencies to use real-world data. So it's definitely possible. In our particular application, that's not even so relevant because we are talking about phase 2 trials, like this is MD Anderson. We don't carry out so many phase 3 trials, but the scientific issues are of course the same. So here's how we want to go about it. A few line summary, essentially talking you again through the scheme that I had already on the title slide with the stylized cartoons there. So what we want to set up is we want to set up an approach that allows us to carry out what we refer to as model-based adjustment of the blue patient population. We want to have a model-based way to adjust the data from the historical trials such that we can then, with some assurance, claim that we have achieved, after the adjustment, equivalent populations. Once the populations are equivalent, then we can pretend that these are just two arms in a two-arm trial. We want to do so because of our particular context with our data. We want to do so allowing for varying number of covariates. I'm reluctant to call it missing data because some of these covariates are missing. Well, they're not there because they were not intended to be collected in these trials, so it's not really missing data. Asking for equivalent populations is asking perhaps for a little more than what's really needed. One of the reasons why we are aiming to create equivalent populations is motivated from another application where we actually talk about 2 synthetic treatment cohorts, and there it's an explicit requirement from the side of regulators to create a situation with equivalent populations. In general, this could be relaxed and we could just ask to understand how the populations are different, try to achieve some level of equivalence, and then adjust for the remaining lack of randomization. We'll still talk about it. That would be in situations like, remember on the title slide, when I showed you the ROC curves, one example was when we fail to create equivalence and we still had like a non-diagonal ROC curve, then we would be in this case. Then we had created some level of equivalence, but we still need to adjust by appropriate pre-processing for a remaining lack of randomization. Now, we are certainly not the first ones. As Sammy commented, this is a popular theme, especially when the real-world data comes from historical studies, when we have data from earlier studies that we could use. One popular approach to use that data is just by way of creating a historical data prior that has been around for a while now. So in that case, we are making use of real-world data only indirectly by creating informative priors that are generally known as historical data priors. Popular approach is the so-called power priors. There's papers by Joe Ibrahim and that's Minghui Chen. The idea is very simple. Use the historical data, short of pooling the historical data with the current data. We use the likelihood factors corresponding to historical data with some fractional power. Using the likelihood with some fractional power, is a formal notion of discounting the information but using it partially, combine it with some original prior, and then the posterior under that model with the fractional power likelihood and the original prior, that becomes the historical data prior for our current study. So power priors are one way to do that. A variation on the theme are the commensurate priors. That's Brian Hobbs and collaborators. Slight variation, while in the original power prior, you still pretend that in the historical data likelihood pertains to the same parameter that we use for the current study. In the commensurate prior, you're explicitly setting up different parameters for historical data and the current data. And then there's just a hierarchical model that combines them as submodels and formally borrows strength, allowing for the possibility that the historical data parameter might or might not be similar to the current data parameters. And this is known as commensurate priors. And the commensurability parameter would be the hyperparameter in the hierarchical model that specifies how distinct the parameters can be between the historical and the current data. Another set of papers set up something which they refer to as MAP priors, standing for meta-analytic predictive priors. The idea is simple and straightforward. They set up a hierarchical model for historical studies. They set up a hierarchical model for related external studies. And in the context of that hierarchical model, they considered the posterior predictive distribution for the parameter in a new study, in a new upcoming study, and that becomes then the MAP prior for our current study. And there is a variation discussed in Schmidli and others, where again they explicitly introduce a notion in the hierarchical model that studies might or might not be exchangeable. It's similar to the idea of the commensurate priors. Discussed it in more detail than what I had planned to. Just want to make the point, setting up historical data priors is certainly one way of proceeding. Another way is essentially to set up a potential outcome framework that's discussed in Tianjian Chu and Yuan Qi in a current Statistics in Medicine paper. Here's what they do. They set up two response surfaces for potential outcomes. One response surface is for like assuming that you have a binary treatment, like say 0 or 1, 0 for control, 1 for experimental therapy. Then there's one response surface, call it F0, for potential outcome when you assign a patient to control. F0 of X is response surface for potential outcome under control, and F1 of X is response surface for potential outcome under treatment for a patient with baseline covariates X. And here's the twist. The response surface for control actually has an augmented argument. It has an additional argument, which is the study indicator S. So S here is a study indicator, where 0 might be the current study, and 1, 2, 3, 4 might be other related studies. And then you use your favorite generic response surface model. Chu and Qi, they use the BART, which is a Bayesian random forest model. And that way they can then conveniently impute a population average treatment effect and make inference about the treatment effect in the current study, borrowing strength by way of these response surfaces, by way of imputing the potential outcomes, borrowing strength across the earlier studies, well, at least for the response surface for control. Several methods, actually many methods, make use of the notion of a propensity score. Many of you know the propensity score is one way of adjusting for the lack of randomization. Usually when you use it for causal inference to adjust for a lack of randomization, you would set up a propensity score for treatment assignment. In contrast here, it's a little different. You set up a propensity score for every patient for being included in one or the other study. So it's a propensity score for a patient being included in the current study, which is say set I equal 1, versus being included in a historical study, which could be, for example, set I equals 0. So it's a propensity score, but not for treatment assignment, for inclusion in different studies. Here's a paper by Meichi Liu and others, also another current stat in medicine paper, which is actually a very nice one because they combine these MAP priors that we just discussed, meta-analytic predictive priors, with the use of these propensity scores in an elegant way. They first stratify the patients by propensity score, again, propensity score for study inclusion. And then within each stratum, they use an MAP prior, a stratum-specific MAP prior, clever way to proceed. And it's actually typical of many of these approaches. Here's Chen and Wang, different Chen than Minghui Chen from Ibrahim and Chen, and others from Johns Hopkins, who also use stratification by propensity score. Then instead of an MAP prior, to use a variation of a power prior, where the exponent is based on, a particularly clever twist, that fractional exponent in the power prior, they base on the similarity of the distribution of propensity scores in that stratum between historical data and current data. So they use the propensity score twice, once for the stratification and then to determine the right exponent in the power prior. Wang and Rosner use the propensity score a little differently. Like there's different ways of using propensity scores. You can use them for weighting, you can use them for stratification, which is saw stratification here, or you can use them by setting up a regression. You can argue if you set up a regression of the outcome on propensity score, then conditional on the propensity score, you can ensure that you can actually make inference on the treatment effect, and that's exactly what Wang and Rosner do. The special twist here is that they are setting up a multivariate propensity score, considering potentially more than 2 studies to borrow strength across. And they are setting up that regression of outcome on propensity score. They are setting it up as a non-parametric Bayesian regression close to my heart. That's why I noticed it. And many others. There's really many of these approaches. There's many variations you can play. A little different, and I only mention it here because it's also in the context of glioblastoma. Alexander, Lorenzo Trippa, and others, they set up a master protocol where many different studies share a common control, and it's not really real world data, but it's still the same theme of sharing controls from elsewhere. So this discussion, just by way of highlighting, we are surely not the first. There's many schemes out there. I would say, broadly speaking, using propensity scores, using potential outcome framework, or using historical data priors. And in the context of this literature, we are trying to contribute yet another variation. In a way, a very simple one compared to some of these methods. Ours is actually a very simple one. Our idea, our intention is, as we had it already in the title slide, what we want to do is we want to introduce weights for the external data. Maybe that's a little similar to what we had in one of the papers, was it Chen and Wang, who had weights. Well, they had weights as the exponent in the power prior. We want to use weights that can be used to actually thin out the historical data. And we want to do that such that after that reweighting or thinning out, you can then claim equivalent patient populations. When we want to introduce these weights, we want to proceed to do that on the basis of a coherent model-based procedure. What we'll do is we'll actually fit mixture models for the current data. Here's again the red current data and blue historical data. We want to fit mixture models to both of these. Many of you will be familiar to the notion when you fit a mixture model that implies a probability model on clustering, because you can always replace a mixture model by latent cluster membership. You can always introduce latent indicators that link observations to terms in the mixture model. And if you interpret those latent indicators as cluster membership indicators, you have a random partition. So many people will use the terms mixture model and clustering almost interchangeably, keeping in mind that a mixture model always implies a random partition, implies a clustering. So we will fit mixture models to current data and historical data, which imply a partition, which imply clustering. And just to stay within the terminology of this literature, let's call the clusters strata, like each cluster is a stratum. And here's what we do. If in the current data we have, for example, these 5 green patients in stratum 1, in the external data, oof, that's a bad example. Can you please jump on to the second stratum, the stratum number 2? We have 3 green patients in the current data and 4 historical patients in the external data. What we could simply do is we could reweight the black patients in the external data by a factor 3/4. Then they would start to look equivalent, right? That's the whole idea. So on the basis of, we'll have model-based clustering using mixture models. On the basis of that clustering, we can introduce weights. Using those weights, we can make the external data look like the current data. That's the whole idea. Important in this scheme is, and that's already clear in that cartoon here, the current data and the historical data, they need to share the same clusters. They need to share the same atoms that define the clusters. We'll come back to that. So they share the atoms, but they have different weights. Of course, that construction is subject to massive uncertainties because there's not a single way of, there's no single way of how you can achieve that clustering. There's lots of uncertainty. And if we want to succeed with our creating equivalent populations, we have to accommodate, we have to account for all these uncertainties. And that's exactly what we shall do. So one more time, I want to rehash the scheme now spelled out as an algorithm. In the first step, we want to fit the data from the red current single arm trial and the blue historical data. We'll do that using a common atoms mixture model coming up on the next slide. See, each time I tell you the scheme again, I make it an inch more formal. On the next slide, we'll have the actual model. In step 2, using this common atoms mixture model, we'll introduce weights to resample or at least introduce weighting for the blue patients in such a way that we can claim equivalence. In step 3, we'll try to prove equivalence. To prove equivalence, we simply merge the red and the weighted blue patients and then try to carry out a classification. If that classification fails, we declare victory, then they are equivalent. And once they are equivalent, then in principle, we could now pretend that these are 2 arms of randomized controlled trial. And in principle, we could use any method to report now inference on a treatment effect.
So Peter, maybe I'll jump in to ask some questions since there are quite some questions accumulated already.
Good. Let me come to the, no, thank you. That's a good moment because after this, it becomes formal.
Exactly, because there's a question very specific to the steps, right? So one audience is asking whether the strata needs to be pre-specified.
Thank you, very good answer. I don't see the question here in my chat box. Oh, here it is, got it, Annie Cheng. Thank you for that. It's a good pointed question. I understood, do the strata have to be pre-specified? Pointed answer to that question would be no. We explicitly accommodate random stratification, random clusters. The question though really I see in the chat here is, do the factors that we use to carry out that stratification have to be pre-specified? Can you rephrase the question, Annie? Do the covariates have to be pre-specified? Pointed answer, yes. Actually, that's obviously a very important step in the whole approach. In the case of that GBM application, we worked with the clinicians to find the set of, in the end, we settled on 10 covariates. That is very important. If these covariates are not pre-specified, you can always add, like if you add sufficiently many irrelevant covariates, any two populations will look different. That said, I should point out though that this is still more general than in our brief literature review, you might have gotten the idea that many just focus on that propensity score. The propensity score is the most brutal way of reducing everything to just a single factor, that score. We are a bit more general. We still allow any number of clinically relevant covariates. In our case, it's 10, but not hundreds or thousands.
Yeah.
And then Frank is asking, is that process retrospective or prospective? I think the correct answer here is prospective. This is something that we do at the design stage. Before we carry out the trial, like when you actually write the protocol, that is when we create that machine. So it's prospective before the single-arm trial is carried out, but we assume that the real-world data exists that we have in hand. That is similar to the power prior thing, or any of these historical data priors. You assume that the historical data is available. Adams is asking, do we create the historical control while the trial is ongoing? Pointed answer, no. The historical control is created upfront at the design stage.
I think one question related to the Frank's one, right? What's the source of the historical data obtained in maybe your application? I think that's what the Thomas is asking.
Quick answer to that question. The source in our case, those are just earlier trials that were carried out in the same department. So they are available. Can I still go back to the previous question, because I think I slightly misspoke. The historical data, like the real world data, that is there, that exists when we at the design stage. But proving then, like the actual creation of the synthetic control arm, that is a process that we carry out once the new data is available. For no other reason to prove equivalence, we merge the two, I told you, right? So we need that data. As we're speaking, there's a new question coming in. After we create the historical control, do we concurrently, once we have the historical data, we don't augment that anymore. But creating the synthetic historical control, that is something that happens at the end of the trial. How to fit data in T when we plan the study? Yeah, you caught me there. That was exactly what I pointed out there. I misspoke. Yeah, the real world data is available at the planning stage. The synthetic control arm that we create, that is created at the end, at the analysis stage. And last current question: how robust is the final trial inference to the choice of covariates? Good question. My guess would be not at all, and shouldn't be, because the covariates better be the clinically relevant covariates. And if we were to fail to select the clinically relevant covariates, it would presumably be inappropriate. So that might be highly sensitive to the choice of covariates. You better select a good superset of the relevant ones. Thank you, all good pointed questions. Yeah. Thank you, Tammy. So keep on watching it and stop me again when there is like a good number of new ones. I think by mistake, I stopped screen sharing. I'll just go straight back. I just wanted to click the chat away, but by mistake, I clicked the screen sharing away. So I told you in step 4, if we succeed in making them equivalent, then we could now pretend we have 2 randomized arms. Sometimes we might be in a situation that we fail to show equivalence. we still have like the backup option of using our model-based inference to carry out now causal inference, like we can adjust for the remaining lack of randomization. And we'll talk about that in the context of the specific model. So I want to now talk you through the specific model. So we need some minimal notation. I'll use I to index the patients. I'll use X sub I for the baseline covariates, which are chosen. They have to be chosen on the basis of expert opinion. One spin-off project that we are considering now is using factor analysis for dimension reduction there. Some of that can be done, but still you need expert judgment to highlight the most relevant covariates. I'll use Y sub I for the response. I'll use rho to indicate generically the clusters or strata, where I use C1 through C cap K to indicate the clusters. So C1 through CK, those are the clusters that are implied by the mixture model. The mixture model does not imply deterministically a set of clusters. It implies a probability model on the clusters. So same thing in different words, it implies a random partition. So these clusters are obviously subsets. They are subsets of, with square brackets n, indicate the set 1 through n. Should have said that. So square brackets n is just the set 1 through n of the patient indices. And a random partition, I'll then simply indicate as generically as a probability model for rho, for the random partition. That's the random element here. Sometimes we'll refer to covariates arranged by clusters. I'll use always asterisk, a star, to indicate anything arranged by cluster. And one more piece of notation, but that's it then already. I'll use script O sub I for the covariates that are available for patient I. I'll need it in the context of discussing missing variables. And script CKJ describes the same thing, just seen from a different side, while script O sub I are the covariates that are available for patient I. Script CKJ are the patients in cluster K that have covariate J available. I'll point it out again when it pops up. Just remember script O and script C have to do with the missing variables. The other important thing to remember is that notation C for the clusters that will keep on popping up. So that's important to remember. C1 through CK, those are the clusters. And here's the model now. It doesn't get simpler than that. I'm just writing down a mixture model. So this is back to the title slide. Remember, I promised you we'll fit a mixture model to the data. Let's start first just with one population, just one patient population, one arm. We are fitting a mixture model to the data. And here's that little twist. I promised you would just be a footnote, and that's all it is. I won't mention it again. In writing down the mixture model, we actually only include the available covariates. Do you see here we have a mixture over the clusters, where in each term of the mixture, we write down a sampling model for the covariates that are available for that patient. This is where we explicitly code a model that only makes assumptions about the available covariates, not the others. The Xi sub k, those are the cluster centers, like the cluster number k has cluster center Xi kj on the Jth covariate. So this actually allows variable dimension covariate vectors. It's one of my pet themes. That's why it pops up here. And then this mixture model, as already advertised, this mixture model implies a partition, actually a random partition. You get a random partition by replacing the mixture model with a latent indicator that links patients to different clusters. And if you interpret that latent indicator as a cluster membership indicator, you have a random partition. And in this particular case, you can even explicitly spell out the probability model for the random partition. I'm skipping here 2 steps in the process. It's nothing difficult. It's totally straightforward. But all I want to point out here is that you can actually spell out the probability model for the random partition. The important thing here is that probability model for the random partition, I don't condition anymore on the size, like the xi, the cluster specific parameters, the cluster centers have disappeared from the conditioning subset. That is because you can integrate out, you can marginalize them. Here in the definition of these G of xk star, I have marginalized them out. Let me keep it at this level, the comment. We are not going to make use of that again. So I just want to point out that the mixture model implies random partition. Actually, it's a random partition that's indexed by covariates. So you could say it is on the covariates. And it can actually be spelled out. I will not make use of the specific expression, so we don't need to dwell on that. So here's again that mixture model. Now I'm being specific. In the previous slide, it was just for generic patient population with covariates xi. Now let's be specific and write down that mixture model for the patients in the real world data, which shall become our synthetic control. And again, the real world data that exists at the design stage and is fixed. The construction of the synthetic control, that happens only at the analysis time when we have all the data available. So at that moment, we assume this mixture model for the blue control data. And this is just copying from the previous slide. And now comes the important thing. We assume the same type of model for the red single arm treatment data, where we have now the red patient's eye from the treatment arm. And the important thing here is that everything has a super index blue or red, except for the cluster locations, the atoms, what I highlighted here in yellow. They don't have a red or blue super index because they are shared. We use common atoms. Now we are at the cartoon from the title slide, where we have a red mixture for the treatment patients and a blue, sorry, it switched to green in the picture, a green mixture for the control patients, for the real world data patients. And it's two different mixtures, but they share common atoms. So it's a common atoms mixture model. Such common atoms mixture models pop up here and there in the literature. Most recently, there was a nice paper by Denti, Michele Guindani and others, 2020 JASA. It's a special case of their model. There's one tweak to that, and I'll not dwell on that, although it's actually important. We do assume that the implied size of the random partition, we do assume that the red clusters are smaller than the blue clusters. Remember when I showed it at cartoon, I first focused on the wrong cluster, and then I said, let me go to the second cluster because we want the blue cluster to be larger than the red cluster, otherwise we can't thin it out. We could still deal with it with appropriate weights, but for this story, it's easier to assume this monotonicity. It's a reasonable assumption. You typically have fewer patients in the treatment arm now than the patients in the historical data that you have available in the real world data. We refer to this model as the common atoms PPMX. PPMX is our, it's just our term for this type of mixture model. We are almost done. Can you still switch back to the previous slide? Let me still jump back one more time to the previous slide. Focusing on this expression that you see now here for the two common atom mixture models, does it sound plausible that if we just focus on the weights on these pies here, if we use ratios of the weights, then we should be able to somehow make the blue patients look like the red patients. It's maybe not immediately obvious. Some details are missing. They're coming up on the next slide. But does it sound plausible now that by reweighting the blue patients with some ratio of those weights pi, we should be able to achieve equivalent populations? That's the idea. And that's exactly what we'll discuss on the next slide. So we'll essentially use a red weight over blue weight to reweight the blue patients such that they look like the red patients. The idea is to formalize it, to make it a bit more formal. What we want to achieve is we want to achieve that posterior integrals with respect to, we want to be able to evaluate posterior integrals with respect to the red population by weighted Monte Carlo averages from the blue population. That's one way of operationalizing that. And claim this can be achieved by using exactly these weights. We'll use weights that are based on the ratio of the red weight over essentially the blue weight. The blue, instead of the blue weight, what I plugged in here is n. Did I ever say that n sub k are the cluster sizes? Yeah, down here it's defined. N sub k is just the cardinality, the size of the cave cluster. Think here of n sub k over n. The n can disappear into the proportionality constant. Then this is just n sub k over n. That's essentially Rao-Blackwellizing the blue weight pi k blue. So here you can see the red weight over blue weight for the mixture model. There's a minor embarrassing detail about it. We can't use that because the pi's are unknown parameters, so we can't use that to reweight the patients. So what we do instead is we take the posterior average of these weights, and the posterior average is approximated by an average over Monte Carlo samples. So that running index M here, index is posterior Monte Carlo samples, and an average of the Monte Carlo samples in posterior simulation under our common atoms mixture model. That is what we use for the weight. At this moment, I just made it plausible. I think it should be plausible that this is the right weight. And we have a few minutes time for that. I will briefly talk you through a formal argument why this is the right thing to do. Like some of you might be a bit uneasy now, like should the right weight be the ratio of the average weights or the average of the ratios? That's not immediately obvious, yeah? What's the right way to proceed there? So here's a more formal argument, just introducing some notation. I'll denote with cap F super C and cap F super T, the mixture models. And within the mixture models, I'll denote with F sub K the kernel for the kth term in the mixture. Earlier, I wrote it explicitly as P of X giving psi sub K. But let's just generically write it as F sub K for the kernel. And important, it's a common atoms mixture, so they share the same kernel. Remember the cluster membership indicators. I might not have highlighted that. But instead of talking about the clusters, it's very common in this literature to instead introduce latent indicators. If I tell you for the IVE patient, a latent indicator in which cluster the patient is, that's equivalent to telling you the clusters, because you can reconstruct one from the other and vice versa. So S sub I are cluster membership indicators. Then let's first focus on that kernel. So F sub K is the kernel. And if we write the kernel, as a CDF, then we could approximate that kernel just by the empirical CDF. What you see there on the right-hand side, it's just the empirical CDF of all the blue patients that are allocated to the cave cluster. So in this line, I have approximated the cave kernel, the F sub K, by the empirical distribution of all the blue patients that are currently allocated to that kernel. So approximating the F sub K by the empirical distribution of blue patients, I can now approximate the red mixture model. I just copied from the second line on top. This is the summation of the red weight pi sub K times the kernel. The kernel are replaced by my estimate of the kernel based on the blue patients. And instead of arranging that sum as a sum over K, and within each cluster having the sum over all patients in the cluster, I can rearrange it as a sum over all patients. And can you see when you do that, then this becomes a sum over all patients where the weight is now that orange WI, where the WI is the red weight over the blue cluster size. And can you read it now as, can you read that last line now, the beginning and the end? Can you read it as, I can approximate the CDF for the red mixture model. I can approximate the CDF of the red mixture model by the empirical distribution of the blue patients when I weight them with that highlighted weight WI. So at this moment, I have shown that I can do that for the CDF. By the usual arguments, you can in the next step show you can do it for any step function. And if you can do it for any step function, you can do it for any reasonably regular function. So at this moment, we have shown that posterior averages for any reasonably regular function under the red mixture model can be approximated by a weighted average of blue patients. And that justifies the use of these weights. Let's pause here for a moment. So these weights are weights that we can use to approximate posterior means of whatever function of interest under the red distribution by blue patients. So in other words, we have set up an importance sampling scheme here. An importance sampling scheme by which we can use the blue distribution as an importance sampling density for the red distribution. The twist to it though was by setting them up as common atoms mixture models, we don't need the ratio of the densities. The ratio of the densities would be a horror. That would require high dimensional or moderately high dimensional density estimation. Instead of using the densities, all what we needed was the ratio of the weights. So we refer to that as density-free importance sampling. So you could say one line summary of what we're doing is we're using density-free importance sampling in a common atoms mixture model to set up a synthetic control. That's exactly what we do. So this was step 2 of setting up the reweighting and thinning, and the rest is actually reasonably straightforward. Step 3 is then the proof of equivalence. Just use any kind of universal classifier. If that universal classifier can't tell them apart anymore, then we declare victory. You might not get victory. If you don't get victory, like the blue line as the ROC curve, then we didn't entirely achieve equivalence and we still have to do causal inference. We have to adjust for the lack of randomization. Step 4, even if we achieve equivalence, it would still seem tempting to use, once you have set up the model, we can use the same model to carry out inference now for a treatment effect. To carry out inference for the treatment effect, I should have highlighted it earlier. The earlier model was only a model for the covariates, for the xi's. The actual outcome did not feature in that model yet. But if we augment the model by a sampling model for the outcome, for the endpoint, remember y sub I was the endpoint. In our particular example, that's overall survival for these glioblastoma patients. So we can say we extend now the model by adding an outcome model for the y sub i's, do the same for the control patients. Now we have actually an outcome model that we can use to evaluate potential outcomes and in the usual fashion get average treatment effect, average over patients to get a predictive average treatment effect. And that's exactly what we do. I can speed up now a little bit and I'll talk you through how it works out in our actual application. In the actual application to the GBM trials, we have data from historical trials over the last, I think the previous 10 years or so they used. They didn't want to use data that goes too far back because at one moment the standard of care has changed. So we have some 300 historical patients, not massively many, but more than what we have in the new single-arm trial. In the new single-arm trial, we have only 49 patients, and we want to use the blue patients to add a synthetic control. That's the intention. The relevant outcome here is overall survival because sadly, these glioblastoma patients, the prognosis is not very encouraging. Like unfortunately, overall survival is not too long. We can consider, for example, now to make inference about treatment effect, you might be interested in a hazard ratio of greater 0.6 versus less than 0.6. That's what our clinical colleagues thought was a reasonable threshold to go after. Sorry, where the lambda here is the log hazard ratio. Since it's not a proportional hazards model, the log hazard ratio is still indexed by time. So the notion here would be it's below or above 0.6 for all time points. Then here we have now, here's now data from a little simulation that we carried out. One simulation which is like a null scenario, where the new single arm trial is set up to have no better survival than the previous trials. And what you see here is these are just one arm is the current treatment arm. I think it's the lowest, it's the bottom one here in that Kaplan-Meier plot. The 5 other plots that you see in that Kaplan-Meier plot, those are 5 different synthetic treatment arms where we simply repeated the procedure 5 times. Yeah, so 5 possible realizations of the synthetic treatment arm, and by construction here there should be no treatment effect. And sure enough, there is kind of no treatment effect. It's not perfect. Like with a little bit of fantasy, you can see some treatment effect here out at 80 weeks or so. But when we do the same now with a simulation where we set up a new treatment arm with a much with a significant treatment effect, like much longer overall survival. And again, you see the that pink one, that's the treatment arm, and the 5 other color ones. Those are the Kaplan-Meier plots for 5 synthetic treatment arms that we set up using the scheme. And sure enough, you can actually see the difference here with that control arm. We carried out some more simulation. Let me breeze through that simulation just to see it looks pretty damn good. So on the vertical axis, we show bias, and the little box plots, the little box plots show box plots of actual bias, where the red one is our method, and the other color box plots are some alternative methods that we use, and it compares favorably. I should say in this implementation, we did use the model-based inference also for additional causal inference adjustment for the lack of randomization if the equivalent patient populations didn't turn out perfectly, but it looks good. And maybe let me just jump to the final slide. So I tried to talk you through a model-based framework using what we called common atoms mixture models. The particular implementation is something known as common atoms dependent Dirichlet process model, which is simply a non-parametric Bayesian mixture model. We used it to adjust real-world data to create a synthetic cohort. Assuming the real-world data is available at the design stage, and the synthetic cohort is constructed upon completion of the trial. The method has limitations. One limitation, and you recognize that acutely in some of the questions. One limitation is the variables, like the selection of the variables really has to be done upfront by clinical judgment. We are thinking currently of using multi-study factor analysis, could be done. It's kind of screaming for it. It's not obvious. You certainly want clinical judgment too, yeah? In the brief literature review, there were some things I missed. For example, Stefan Vance, Lorenzo Trippa, and others, they have a nice current paper where they actually go kind of one step further, and I liked it. They used the historical control for interim analysis, which is an interesting variation of the theme. Sijin Golchi has a current working paper where she also uses a notion of similarity. She uses that to put it in the exponent of a power prior. And I just want to point out, kind of, if I had to make a one-line summary of what we did at a slightly more formal level, I would say this is the one-line summary. we set up a common atom mixture model, and the ratios of these mixture weights are used for resampling to create equivalent populations. We also think of this simply as like density-free importance sampling. One of our next projects is these same weights, they could actually be used potentially also in a totally different context for setting up a study for a diagnostic test, like for biomarker discovery. For validating a biomarker panel, but that's a whole other talk. Thank you. That's everything I wanted to tell you today. I think we're almost on time.
Yeah, thank you, Peter. Really appreciate it. There are a few questions. I know we're kind of a bit out of time, but if you can briefly answer some of the questions in the list, will be great. So I think audience is really anxious. Thanks.
So let me start with the last question. What are the criteria for determining the bias? I really jumped over that. Like I essentially skipped the simulation things. I just showed you the pictures, and I think it's that bias that you're referring to, right? This was simply bias in the treatment effect. Like under the simulation setup, there we had a true treatment effect, and we just recorded the bias in repeat simulation. Thomas is asking, can site be a covariate? Good question. It didn't arise for us because all our real world data comes from the same institution. Cheap answer, yes, it certainly could. Longer answer, that could be a delicate one because certainly site would be an important effect. But so quick answer, yes. Michael is asking, what do you do if a cluster appears in the test sample, but not in the control population? Embarrassing question. You cut to the core of one of the assumptions in our model. Remember, I tried to sneak in as a footnote, I tried to sneak in that assumption. We assume that the red clusters are always smaller than the blue clusters. By that assumption, this should not happen. So my cheap answer is that is not allowed to happen. A little bit more serious answer, we added as a constraint in our common atoms mixture model. It should not happen. Like this is similar to the usual assumption that you have to assume that the propensity score is bounded away from 0 and 1. Like you need overlapping support of the two populations. Someone is asking, in step 1, does the partition size need to be the same for all partitions? No, that's not required. Thank you. Good question to ask. Yeah. It's possible that the blue partition, like the number of terms in the blue mixture, could actually be larger than the number of terms in the red mixture. That's totally fine. Not the other way around, though.
Yeah. I think, Peter, that's all the questions so far. The previous one you already answered. I thank you so much, Peter. It's a great presentation, and you can see audiences are so engaged in your presentation.
You keep your speakers on the toes. Yeah?
They asked a specific and actually right to the point question. I really appreciate you and also the audiences for all together. And thank for all volunteers to make it happen for us for this session. Thank you guys so much. Have a good one.
Thank you. Thank you, everyone. Thank you for joining.
Thank you, Peter.
And thank you for all those pointed questions. They were all very good. Yeah.
Yeah.
Thank you.
Good questions. Bye, guys.
Good weekend, everyone. Bye.
Bye.
All right. Thank you, Peter. Have a good one.
Thank you. Thank you. So you're going to post copies of the slides that I sent to Mitzi?
Yes.
Okay.
We'll send it to our YouTube channel.
Perfect. So anyone asks, I can post. I can point. Yeah. Thank you. Bye.
All right. Have a good weekend. Bye bye.
You too. Thank you. Bye.
And for all.